gravitational wave detectors that are working fully operational right now. These things are, the arms of this thing are 4 kilometers on a side, and what it's working to detect is it's working to detect ripples in space itself that are formed not only by the presence of a black hole, but where 2 black holes merge and collide. And so when that happens, or when that burst of gravitational radiation comes past the Earth, everything inside kind of wobbles, or everything that passes sort of wobbles a little bit like a jelly. And we can measure very accurately the differences in the lengths of these 2 arms. They change by about 1 part in a million trillion, the length, which is much, much less than the width of a single atom. With lots of cunning optics and various other things, we can actually see these changes exactly. So LIGO sees, what LIGO sees is the most intense way we know to generate gravitational waves is when 2 black holes meet each other, merge, and form a single black hole. And so what LIGO sees, and so the first detection was in 2015, what LIGO sees is something like that. So on September 14, 2015, and 09:50:45 UTC, both of the LIGO detectors were simultaneously operational because you want to be able to rule out local, truck driving past might fake what looks like just the vibrations, or even pretty much anything you can imagine. But if you have 2 well-separated detectors, you can not only rule out local effects, but you can also start to get a sense of where these objects happen over the sky, because one of them will see this event a split second before the other. And so what LIGO sees is something like this. So this is the 0.6 of a second. We've got 2 black holes that are orbiting each other. As they orbit, they emit gravitational waves that causes them to fall close to each other, like a satellite around the Earth that gets slowed up by the drag in the Earth's atmosphere. It comes closer to the Earth, it moves faster, and this process speeds up. So you can see the gravitational wave signal down the bottom. It's growing in amplitude, but also growing in pitch. The peaks are getting closer and closer together, the pitch is getting higher. So this is the last 1/10 of a second. You're doing it now. They're going to kiss. We're going to have 2 black holes to 1. It's the last burst of gravitational waves. Single black hole. And then the ring out at the end. So this must, if Einstein is right, this must be a pure black hole, because the resulting black hole that we form is going to inherit the spin that these 2 objects had as they orbited one another. This pulse of gravitational radiation leaves, heads out into space. So this particular, the first one we saw was maybe in motion for 1 billion years. So not only before, not so much before there were dinosaurs on Earth, but before there was even multicellular life on Earth, this event took place. We see this moment for 1/10 of a second, and we detect what's going on. It turns out these 2 black holes started out at a mass that we can work out from the signal we see of 36 and 29 solar masses. What's left over is 62 solar masses. 36 plus 29 is what? 65. And so there's 3 solar masses of missing matter, which has been converted into energy as during this merger phase. So at 1/10 of a second, you've radiated 3 solar masses converted to energy by equals mc². So the brightest object in the universe is this pair of black holes for that 1/10 of a second. And not only is it the brightest object in the universe, it's actually radiating energy, more energy in that 1/10 of a second than the rest of the universe put together. All of the stars in the universe are generating less. So if we could observe gravitational waves with our eyes, we'd suddenly see this flash. One part of the sky would go dark, and then a few months later again we'd see another flash as one of these things went on. So we can do that. We can even imagine what the signal sounds like. So this signal is if this was a sound wave, we'd be able to hear it. It's in the right realm of human hearing. So you hear something that goes like, and it gets brighter, and then it gets cut off. So what you're actually trying to do with this is everyone goes like sort of mumbles to themselves, and somebody somewhere's going. And so the job of LIGO is to pick out the from the mumbling that's happening everywhere in the room. And so most of the mergers we hear are going to be, and the mumbling's pretty loud. But over the years, LIGOs, but the builders of LIGO have been able to make a more and more sensitive instrument that essentially washes out or reduces the amount of noise in the instrument itself and makes it less sensitive to the noise in its environment, so it can be more sensitive to what we hear. So that gets us to, so LIGO, that was 2015. Over the next few years, LIGO reported a handful of gravitational wave mergers. And so they were what they call gold-plated events. They were events that kind of popped out of the data. When you looked at it, they looked at it every which way they could, and then they would release these single events one or two at a time. And the other way that LIGO made itself famous was that the other thing it saw was not the merger of two black holes, but the merger of two neutron stars. And so the key thing is, unlike a kind of Mitchell black hole, where you've got like this giant ball of honey that just happens to be inside of its own, whose escape velocity is greater than light, a black hole is entirely empty, other than the single mathematical singularity of the center. So when two black holes merge, there's nothing to collide. There's no, it's just empty space passing through empty space. So all you see is the gravitational phase. But if you look at a neutron star, which is this end state of the sort of star somewhat bigger than our sun, will collapse to the point where the electrons and the protons are going to be joined back together. So all you've got is this ball of neutrons. And, if the sun was a couple of times bigger than it is, it would form a neutron star that was maybe 15 or 20 kilometers across. So only slightly larger than the radius that we have as a black hole. But if you take two neutron stars and you collide them together, then they will collide, their orbits will inspiral to the same reason as two black holes will inspiral. But when they collide, you've got two physical objects colliding and you're going to produce a flash of light. Huge flash of light. So this object here, this is a galaxy NGC 4993. And it's about 140 million light years from Earth. And that little red dot there, this one here, is not normally present in NGC 4993. And what that is it's what's called a kilonova. So it's not as bright as a supernova, but it's reasonably bright compared to the galaxy as a whole. And that's the product of merging two neutron stars together. And the reason we knew where to look for it is not only did we see exactly that signal in LIGO, or the signals that you expect from a neutron star merger, but also there was then at that point a third gravitational wave detector in operation, which gave you a better sense of where it was in the sky. But on top of that, 1.8 seconds after the gravitational wave signal, you also saw a flash of gamma rays that corresponded to a gamma ray burst that was associated with this, that came from the same part of the sky as this event. So in this case, you're seeing an object in both gravitational waves in LIGO, but you're also seeing an optical light, in the case of this image here, seeing it in gamma rays, seeing it in radio waves, because you've got two physical objects that are actually related. So this was the first, and up until recently, only neutron star merger that had been observed in a gravitational wave. So okay, this is roughly where we are now. If I was giving this talk at the beginning of the year, this is where I'm. So to show what we've got now, firstly, we've now got three gravitational wave detectors that are operating. Two LIGO detectors, and in Virgo, which operates in a similar way to the two LIGO detectors that is located here. Given three detections, we can actually do a pretty good job of pinning down the position of an object on the sky if it's sufficiently bright. So on top of that, LIGO was offline for most of 2018, and they tuned its sensitivity a little bit, so it's about maybe twice as sensitive as it was before. But because we're just seeing the brightest events that kind of stick up above the noise, if you lower the noise level ever so slightly, then you're seeing more and more events than would be the case. So a little reduction of noise produces a big improvement in your ability to see. The other thing that LIGO is doing is it's actually releasing now in real time the candidate events that it sees with about a 10-minute delay. So you can actually sign up to a Twitter feed that will tell you where these things are. And you can see that since April the 8th, you can see there's been half a dozen or more candidate events. A couple of these will probably be noise when you come to look at them properly, but we've seen almost as many gravitational wave events in the last 15 days as we saw through the course of most of the year. So in fact, thanks to the fact that these things have been made more sensitive. If you go, the next iteration in sensitivity, we're going to be seeing these things every day. Yes?
Does it run all the time, or do you fix and stuff?
They try to run it continuously, but it's very, they have what they call locks, so there's all sorts of reasons why it can have kind of glitches or so I think once everything's kind of locked down, then they have a reasonable amount of uptime. But you're talking you still have reasonable amounts of time where one or more of these detectors is locked. In particular, we've seen evidence for another neutron star merger. So you can go online and you can see, for instance, a map where it might be, which is generated. You can do a better job of this map when you go back and crunch the numbers again. You wouldn't want to necessarily try looking for this one in the sky because you can see that it covers a big patch of sky. The stronger the signal, the better job you can do of putting it down. The other thing they do is they produce a kind of guesstimate of whether or not whether it's noise, whether it's a neutron star merging of the black hole, whether it's a binary neutron star or a binary black hole merging. So they can also produce something that looks like this. And you can actually log into this here. Okay, so we're learning tons of things. We're seeing more neutron star mergers than we might have guessed. We're seeing lots of big black holes. The big black holes we're seeing were once big stars, so we're learning something about the first generation of stars that existed in the universe. And we're also learning that Einstein's doing pretty well. Which is good. Okay, the other thing, but wait, there's more. The other thing that I was asked to tell you about was how many people here heard about this Event Horizon Telescope? Half of you, okay. So this is completely different. So gravitational waves, one of the things you learn about first there was optical astronomy, but we didn't call it optical astronomy because it was just astronomy. But then we have radio astronomy, we have gamma ray astronomy, we have infrared, all these different things. All of those things are different flavors of light. But gravitational waves are something that they're ripples in space itself. They're not made out of light. But the Event Horizon Telescope is a radio telescope. And the reason it's in the news is not because there haven't been radio telescopes before. The reason it's in the news is because it's a network of radio telescopes that were designed to go after the two black holes that look the biggest when we see them, that we know of when we look at them on the sky. And the image that everyone's returned is this one here. It looks sort of like a glazed donut. So if you're an astrophysicist, front page of the New York Times above the fold is where you want to be. That's what these guys have pulled off. And so what they've done is this announcement was on April 11th of this year, but we've known for several years this collaboration of telescopes has been in operation. So what it turns out that the two galaxies, or the two black holes that are easiest to see from Earth, or as look as big as they are from Earth, one of them is the black hole in the centre of the Milky Way, which is by far the biggest black hole we think will be in the Milky Way, which is about 25,000 light years from Earth, 4 million times the mass of the Sun. The next biggest black hole, not in terms of its mass, but in terms of its apparent size in the sky, is in the centre of this galaxy, which is M87. So this galaxy is 55 million light years from Earth. It's in the constellation Virgo. It's the centre of the Virgo cluster. Its central black hole has a mass of about 2 billion times the mass of the Sun. So that's about 1,000 times bigger than the Milky Way's black hole. This black hole's about 1,000, therefore about 1,000 times bigger in radius, it turns out, which means it has about the same size on the sky, even because it's about 1,000 times further away. So the Event Horizon Telescope. So this is one of the biggest galaxies in the universe that we can see. So this is possibly one of the biggest black holes anywhere in the universe. So the Event Horizon Telescope is an array of radio telescopes dotted around the world. When these observations were taken, the Greenland telescope wasn't fully online, but you can see there's one at the South Pole, literally at the South Pole. There's a bunch of them, one in the Atacama Desert, one in Hawaii, a couple in Europe, and then some on the west coast of the United States. They don't all observe simultaneously, but the observations are processed offline. And so they literally carry an object. So this is the computer that's used to crunch the data. And they literally carried something like a ton of hard disks from around the world and then brought them together in order to carry out the data analysis. And so this image here of Katie Berman, she's one of the people who worked on this analysis, and you can see that there are just these huge stacks of hard drives, so petabytes of data. What they did is they used this technique called very long baseline interferometry, so that the set of telescopes they had effectively worked as one giant telescope. And the things that control, if you've got a 6-inch telescope as opposed to a 12-inch telescope as opposed to a 10-meter telescope, the thing that improves the resolution of your telescope is the size of the telescope. And then also the more glass you've got, the greater ability you've got to catch up. The other thing that controls your resolution is the wavelength that you're using. The shorter the wavelength of the same size telescope, the better resolution. So what these guys did is they basically had strung together this kind of artificial radio telescope that's got the same diameter as the Earth. So you couldn't build a bigger radio telescope and have everything sitting on the ground. They're also working for radio astronomy at a relatively high frequency of about 200 gigahertz, which is, means that they've improved their resolution, and given that, they can get micro-arc-second resolution on the sky. So when we look at the central black hole, what we're looking at is something like this. So this is from a movie that these guys made. You can download it. So snags and frames. So this is what we think would look like the central black hole at the center of M87. It's got an accretion disk. It's also got a jet coming out of it. So it's got this something like this. It's got this bright pool of light coming out of it. And so what we can do is we can zoom in on the center, just the very center of that black hole. And what you see is something that looks like this. So as the light tries to leave the vicinity of the black hole, it can't fly in an exact straight line, and it gets bent. So you can actually see photons coming out of the black hole, coming out from the neighborhood of the black hole, that have been pretty much turned through 180 degrees by the gravity of the black hole before they escape. So rather than seeing this kind of fuzzy cloud, what you actually get is this much more complicated image. And so when we see, if we zoom in, we can see even photons that are sort of producing this much more complicated shape. And then we say, well, we account for the fact that our detector is going to be pretty fuzzy. We expect to see something like that. And so the space in the middle is effectively the shadow of the central black hole. And what we're seeing is light that has, once we take this ring of gas around the black hole that has a temperature of billions of degrees Kelvin. Once we look at that, what we're going to see is we're going to see this kind of complicated pattern where you've got brighter at one side, fainter at the other side, and with this elliptical space in the center. And so this isn't exactly the event horizon of the black hole. It's a space about 20 times larger, but what we're able now to see is not in the case of our own galaxy, where we can see a black hole that's light hours from almost a light day from the central black hole. In this case, we're looking at gas and dust that's really in the vicinity of the event horizon itself. So the cool thing about this result, and the reason it gets into the newspaper, is not that it's, in fact, what they saw was pretty much what we expected to see. So exactly the same as LIGO, the first detection from LIGO was actually confirming our expectations for how it is the gravitational wave is going to behave. This image actually confirms our expectations for what we expected to see in the vicinity of the black hole. The question isn't so much what we've learned we can do it. The question now is what are we going to do next? So for now, this is almost what you might call a proof of concept. They've taken data from the Milky Way, but they haven't been able to image the central black hole. They've got more data from a second observing ray. But now, for the first time, we're looking directly at the environment of the black hole itself. And also, if you want to do better than this, the only way we're going to build a more accurate telescope is to actually go into space. So this produces a case for space-based variable baseline astronomy. Is there any questions about this?
I had one thing not to do with the physics or anything, but I thought it was interesting when the first LIGO announcement was made, there'd been leaks on the internet in the week or two before.
Yeah.
The other, whereas this team seemed to keep it completely
They did
quiet.
I think they kept it better zipped. The one guy in particular leaked the LIGO data. I mean, lots and lots of people have heard it, but I think that there was one person who couldn't resist. I'd heard the story and I thought, I could become Twitter famous if I and I thought, no, thousands of people have worked really hard for years to do this. I'd be at one point. What's the name? I did that, but it turned out one of my colleagues was it. What's his name? And he did. Yes, there's a question about.
This is a bit off subject. If you consider the case of